So now that we've gone through all the postulates up to postulate 5 and we understand projection operators and that, we're in a position to analyze those final few Stern-Gerlach experiments we introduced at the start of this semester. So let's go ahead and do that. So first of all, remember the third Stern-Gerlach experiment. We had a beam of particles, spin 1/2 particles coming out of our oven, totally randomized, and we prepared a state using a Z analyzer so that all of the beam coming out of that spin up path was sort of our initial beam, right? So we have this spin up beam, and then we sent that through a Stern-Gerlach analyzer aligned in the X direction. And we can ask, well, what's the probability of measuring of the beam coming out as a spin up, as a particle coming out of that X Stern-Gerlach analyzer's beam up? And we know that from postulate 4 that the probability of measuring a spin up in the X direction is equal to the inner product of the spin up in the X bra with the beam, the particle state going into that analyzer, squared. So when we do that, we want to be in a single basis when we're doing this. So we want to write the spin up in the X bra in terms of our Z basis states, which we know looks like this. And then we can just use our Dirac-Brock-Het notation and the fact that the spin up and spin down in the Z direction states are orthogonal. We can just carry out this multiplication, this inner product, and we get the 1 over root 2. The spin up inner product with itself is 1. The spin down inner product with the spin up is 0 because those states are orthonormal, and we get the probability of measuring a spin up in the X direction is 1/2 or 50%. And that's what we see. That's what we saw when we went through this experiment. Half, it was totally random. Half of the beam, half of the particles coming out of that X Stern-Gerlach analyzer were spin up in the X direction, half were spin down. So now that we know there's essentially a 50% chance that spin up in the Z direction beam going through the X aligned Stern-Gerlach analyzer will result in a spin up in the X direction measurement, we can ask what state is the beam in after that X Stern-Gerlach analyzer. In our previous discussions, we mentioned and discussed, so we already know that this is going to be in a spin up in the X direction, but this is a good chance to actually look at postulate 5 that we discussed recently in the last few video lectures and actually apply it to this situation to see how that works, right? So postulate 5 was essentially this: the state of the system after some measurement is the normalized state of the initial state, the spin-up state, projected onto the eigenstate that corresponds to the measured eigenvalue, right? So that's what's shown here. We have the initial state, the beam coming in was spin up in the X direction, and we use the projection operator for the spin up in the X direction because that's the beam that's coming out. We know that projection operator is just the Ket and Bra outer product of that state. So plugging that into our postulate 5, we get something that looks like this. Now, in this Bra-Ket notation, we want to be using the same bases. And if we look at that spin up in the X direction, Bras and Kets in there, that's written in the X bases. And we want to use, right now we're using and familiar with the Z bases. So we can remember that the Bra for spin up in the X direction can be written in terms of the Z bases this way. Similarly, the corresponding Ket can as well. So that projection operator into the spin up in the X direction state can be written, you just make that substitution. We have the 1 over root 2s, one for the Bra, one for the Ket, that make 1/2 times those Ket and Bra combinations. We just do the same way we would do standard algebra, and we end up with that projection operator being 1/2, this sort of expanded operator that is essentially the projection into the spin up with the spin up ket and bra, the spin up ket with the spin down bra, the spin down ket with the spin up bra, and the spin down ket with the spin down bra. If we substitute that in for the projection operator in the projection operator of the spin up in the x direction, we can see that when we're operating on it with this spin up in the z direction ket that we have from postulate 5, the only terms that are going to be non-zero are the ones where we have a spin up bra operating on a spin up, that spin up ket. So this term and this term are the only non-zero ones. So the state after it comes out of that Stern-Gerlach analyzer is this. And we know that that inner product, because those things are orthonormal, is just going to be 1. All those spin-up inner products are 1. So this ends up being essentially 1/2 over 1 over root 2. We see that this just simplifies into the x spin-up state like we saw. But we've gone through the gory detail of actually applying this somewhat straightforward case with the full sort of all the details of postulate 5 to get that. But what we see is kind of exactly what we knew when we first looked at this. We have a 50-50 chance that that incoming spin up in the z direction state is measured as spin up in the x direction or spin down in the x direction, and that if it was measured as spin up in the x direction, it is in the spin up in the x direction state after measurement. Now that we're in this spin up in the x state here, what is the probability that when we send it into this final Stern-Gerlach analyzer aligned in the z direction, that we end up with measuring a spin-up state, getting that eigenvalue of positive h bar over 2? Well, we know from postulate 4 again that the probability of that measurement outcome, the spin-up, is just the inner product of that spin-up measurement eigenvector with the incoming state, in this case, the spin up in the x direction, all squared. We know that that spin up in the x direction, written in the z bases, because we want to be in a single basis, can be written as that. So when we make that substitution and carry out that algebra, the math there, we end up with this sort of expansion of that. The probability of measuring that spin up is 1 over root 2, the inner product of spin up with spin up, plus the inner product of spin down with spin up. Since those are orthonormal, that ends up just being 1. So we have 1 over root 2 all squared, or 1 over 2. So knowing that we are in the spin up in the x direction state going into that Stern-Gerlach analyzer, we've just shown that there is a 50% chance that the result of the measurement in the z direction with that third Stern-Gerlach analyzer the result of that is going to be spin up. 50% chance of it being up, 50% chance of it being down. So where does that leave us, right? So what's the total probability of measuring that spin up state after going through all these Stern-Gerlach analyzers? Well, we have 100% of our particles in that spin up in the z state after our state preparation. The probability of coming out of that x Stern-Gerlach analyzer, it was P1, we'll call it, and then that was 50%. The probability of that state then coming out, going into the Stern-Gerlach analyzer in the z direction and coming out as spin up again, that was 1/2. To get the total probability, we would just multiply those probabilities together, and we would get 1/4 of the initial particles that go in that first beam come out that way, and that's what we saw. So this sort of makes sense. You take the probability of each individual step, multiply them together, and you'll get the total probability of them both happening. Turns out if you take the lower path, sort of, if after the x Stern-Gerlach analyzer we took the spin down state and put that into the z-aligned Stern-Gerlach analyzer, it doesn't change much. It's 1/2 times 1/2, we get 1/4. And that's what we see. This brings us to experiment 4, where we have, they had these three different setups. So A was what we just analyzed, state preparation in the Z spin up state. That's 100% of our beam. Coming out of the X Stern-Gerlach analyzer, 50% of our beam goes spin up, and we can feed that into the Z, the third and final Z Stern-Gerlach analyzer, and 50% of that, 50% goes up, 50% goes down. So we get, a quarter of our initial beam measured at the end as spin up in the Z, and a quarter of our initial beam measured as spin down. And as we mentioned just a second ago, had we chosen the lower path, the spin down out of the X Stern-Gerlach analyzer, we would have got the exact same result. That doesn't change anything. So experiment 4 was really, okay, what if we take both of those paths, and we don't really look at them, we just coherently bring them back together as one input into the Z analyzer. And we saw something very weird when we looked at this, in that 100% of those the results were spin up in the Z direction. So in A and B, we measured the spin angular momentum in the X direction in that middle step. In C, what if we don't actually measure that? We just kind of bring them back together. Turns out that when we don't measure it, we don't lose that information that we previously had from our initial Z Stern-Gerlach analyzer. So let's go through and actually analyze that. What do we have here? Coming out of the first state preparation, we have spin up in the Z direction state. That's our entire 100% of our beam. What is the state after that Stern-Gerlach analyzer aligned in the X direction? Well, postulate 5 says that the state after some measurement is just the projection of that input state onto the eigenvector that corresponds to whatever the outcome was, all normalized. In this case, the input ket is the spin-up ket, because we've prepared it with that first Stern-Gerlach analyzer. And the result of that is we're taking both the spin-up and the spin-down measurement results, and we're not really measuring them. We're just curving them back together into the same beam in some coherent way. And so the projection operator is projecting onto both of those kets, so it's just the projection of the spin up in the X direction operator plus the projection of the spin down in the X direction operator. We can write that in terms of the outer products. Those projection operators are just the ket-bra outer product of those states, so we have both of them. And if you recall from our previous video lecture, that the completeness relation showed that the sum of those two projection operators is equal to the identity matrix. And if we use that relationship, this state afterwards sort of becomes trivial. The identity operator acting on any ket just returns that ket. So what we end up with is we still have that Z spin up in the Z direction ket as our ket. So when we figure out the probabilities of the third Stern-Gerlach analyzer measuring spin up or down, given that this is its input ket, they become trivial. We have up, up. The inner product of spin up and spin up is 1, and it's because it's an orthonormal basis, and spin down, inner product of spin up is 0. So we get the results that we see. 100% of our beam is measured as spin up, 0 is measured as spin down. So let's look at that sequence of sort of measurements we've described and see again why that result is weird. So let's look at the probability of our final measurement having the result of spin down in the Z direction, right? When we look at the probability along the upper path, so we take the output of the spin up in the X direction, feed it to our Z Stern-Gerlach analyzer, we end up with a quarter of our beam ending up at our spin down path. If we look at the lower path, so we're coming out of the spin down out of the X direction in that middle Stern-Gerlach analyzer, we get the same thing. We get 1/4 of our beam going as spin down. If we look at when we have the possibility of both paths going into there, we get 0% of our beam reaches spin down, which is really weird. That's not how we would expect the probabilities to behave. If well, there's a quarter of the beam can make it through this upper path, a quarter of the beam can make it through the upper path. If we open both paths, we would expect a half of our beam. We would expect to just add those probabilities together. That's not what we see. You're probably familiar with one of these famous quotes from Einstein that are paraphrased as God does not play dice. This was, a comment referencing his being uncomfortable with the not being able to deterministically predict the outcome of a given measurement. This is the whole idea that that X Stern-Gerlach analyzer, say half of the particles would come out spin down, half would come spin up, but there's no way of predicting each individual particle. That would be totally random. That troubled Einstein. I think this is actually much more weird than that, non-deterministic sort of method. It's to quote Scott Aronson, it's not that the weirdness isn't that God doesn't play dice, but it's rather these aren't even normal dice. We don't add the probabilities of two different paths when we open up. We see much weirder things going on. So let's look a little deeper at what is actually going on. How can that be? And I mentioned way back when in a much earlier video lecture, it looks a lot like interference fringes in light. And so if we want to look at the probability of measuring that spin down state in that final Stern-Gerlach analyzer, well, the probability of that last measurement is just the inner product of the eigenvector of the measurement result, that spin down, with whatever that input state is. I'm calling that psi2 in this case. We just showed a few slides ago that input state is that spin, is sort of the mixture of that spin up and spin down in the x direction state. So I'm going to write it this way. So when we take that inner product to get that probability, we can expand it in this way. And if we take that and then square it, like we do to determine the probability, we get, we have to take complex conjugates in that, but we get this. We get the first term in this is the spin down and the spin up in the inner product of the spin up ket in the x direction and that complex conjugate, spin up in the x direction and spin down in the z direction, plus down, down in the x, down in the x, and down again. And then we have this third term, all the cross terms over here on the right that result from squaring these two things. And if we look at what those actual terms are, that first term is just the probability on the upper path. Remember, these inner products aren't giving us probabilities, they're giving what are called probability amplitudes. And the fact that we're adding those amplitudes before we do the squaring means what we get after we square everything is the first term is just the probability along the one path, the second term is the probability along the other path, and we have all of these extra cross terms or interference terms that can actually, because these are complex numbers, probability amplitudes, they can be negative and they can actually make the total probability go down or up relative to just summing those two probabilities. So again, we have this weird sort of interference type effects that we can see in these quantum systems that I think is just incredibly interesting and very useful in a lot of fields of quantum information processing.